Hello, and welcome to Becker Breaks It Down. In this episode, we are actually going to formally prove that a quadrilateral is a parallelogram. Okay. And we're going to do so without using the property that both pairs of opposite sides are congruent. Ooh, so we have to go around that. Okay. So we are given that AB is congruent to CD and that BC is congruent to DA. We want to prove this is a parallelogram, but we can't use both pairs of opposite sides are congruent. So what else can we do? All right, maybe you're thinking congruent triangles, and you're also seeing, hey, there's a shared side. So we can say that BD is congruent to itself. Of course, that's reflexive. And then that gives us the three congruences we need to prove that triangle ABD is congruent to triangle CDB by side. Right. And so congruent triangles are useful because once two triangles are congruent, we can use CPCTC for the remaining congruences. So what would be useful to us here? Okay. All right. So we could use the fact, the angles are numbered for a reason, so they probably want us to use them, right? So we can say like angle 1 is congruent to angle 3 by CPCTC. We could say the same thing about angles 2 and 4, right? So we can say that angle 1 is congruent to angle 3, and that angle 2 is congruent to angle 4 by CPCTC. You may be wondering why. Why should we say that both of those pairs of angles are congruent? Okay, and the reason is this. Remember, congruent angles can help us prove parallel lines. In a quadrilateral, that's a parallelogram, both pairs of opposite sides are parallel. So if you look, here's angle 1, and here's angle 3. The fact that angle 1 is congruent to angle 3 allows us to prove that AB is parallel to CD. Likewise, the fact that angle 2 is congruent to angle 4 allows us to prove that BC is parallel to AD. And so that's by the converse of the alternate wonderful. It's by the converse of the alternate interior angles theorem. Okay, thus ABCD is a parallelogram by definition of parallelogram. Parallelogram, that's how I abbreviate it. Definition of parallelogram, right? We could have simply used one of those two sets of parallel lines in step 6, and we could have said if one pair of opposite sides are parallel and congruent, it's a parallelogram. So either way would have worked. Okay, but the key and important thing here is to remember that we can use congruent angles to prove parallel lines in a parallelogram. Yeah, that is probably going to be really useful to us. Okay. This one here is a little bit more complex. So to help us out, they've kind of given us a flow diagram, okay, to get us thinking about things. So like we were given that AF is parallel to EC. Okay, so here's AF and here's EC. And so there are a couple of things that you could do with that, but I would lean towards angles 1 and 4 there because they are right there and angles are numbered for a reason. So we could like totally say that angle 1 is congruent to angle 4 because these are alternate exterior angles, right? We were also given that AF is congruent to EC and that BE is congruent to DF, which is a tad too long because it would be nice if BF were congruent to DE, you know, because then I could work with these two triangles, right? And the truth is that can be proven. We haven't really done that, but you know, if you were to, from these two congruent segments here, if you were to subtract that segment EF from each one of them, what remains would be BE. And we can say it's congruent, I'm sorry, BF. And we can say that's congruent to DE. And this is something known as the segment subtraction property. So then I can prove, well, I just proved that BF is congruent to DE. And that allows me to prove that those two triangles, AFB and CED, are congruent. And that's useful because then CPCTC would allow me to say like that angle 2 is congruent to angle 3, which would prove if angle 2 is congruent to angle 3, that would prove that AB is parallel to CD. And then I can use a second CPCTC step to say that AB is congruent to DC. Okay, so now what we have here is the same pair of opposite sides that are parallel and congruent. And so we can say ABCD is a parallelogram because one pair of opposite sides is parallel and congruent. I'll let you formally write it out in the two columns. Okay, but I just wanted you to see another example. And that's how Backer breaks it down.